Welcome to this FP2 video on first order differential equations with separate variables. Now, a lot of what we do in this video will be familiar. Okay, you might not have known it as differential equations before, but it'll be very familiar. So we'll do a few examples and just a few questions to practice, and there will be more to learn as this topic goes on. But basically you're going to be given like a first order differential equation, okay, and it's generally going to be written in the form of dy by dx equals, and then some function of x and some function of y. And of course these are, they could be anything. It could be dx by dt, for example, like a parametric equation, a dy by dt, and these would be functions of x and t or functions of y and t and so on. Okay, it could be u and v, but in general it's going to be y and x. And the way you solve these is basically, although it's not entirely true, okay, like you can't just multiply by this dx, it does work out in that kind of way. Okay, so in this case, I would take my g of y to the left and dy, and then I would leave my f of x on the right and take my dx up there. So that's kind of what I'm doing, although mathematically that's not exactly what's happening. Okay, you can think of it that way when you're solving these problems. So, sorry, the g of y would be 1 over g of y. Okay, because we're dividing by this function when it goes to this side, and we're multiplying by this dx. And like I said, that's not mathematically what's happening, but that is how you can think of these. Okay, so take everything with the y to the left side with your dy, and then everything with the x on the right side with your dx on the top, and then you've got your integral signs. So you'd integrate this function with respect to y and this function with respect to x. And sometimes you might be asked, so you'll basically solve this and get a general solution. The general solution will be like plus c, for example, so constant. And you may be asked to sketch curves that are called a family of solution curves. Okay, sometimes you're given, values for that. That is just a few examples where you can set c to be, 0, 1, 2, -1, -2. Okay, just to give some examples of the curves. Okay, but generally I haven't seen that in an exam asking for sketches of a family of solution curves. So I will go through it when I do the examples, but I won't be kind of writing questions with it. And then in some situations you're given the boundary condition so that you can find that constant, and then you're finding a particular solution. So the general solution is going to be with a constant, and then the particular solution is when you basically find the value of that constant for that particular solution. Okay, and that's kind of all there is to it. So let's jump into the first example. So a nice easy one. Find the general solution of the differential equation dy by dx equals 3. So that now separates to dy on the left and 3 dx on the right, and then we put our integral signs in. And integrating the left, I get y, and integrating the right, I get 3x plus c. And this is now my general solution. And if I wanted to sketch members of the family of solution curves represented by the general solution, I would have, this one when c equals 0. This, for example, when c equals 1. Or this when c equals -1. And, I can go on, where c equals -2. And so on. Okay, so that is just some examples of the family of solutions. And of course we can work out the values in which they cross the x-axis here, and I could put those in if I needed to. Okay, like so. But this is the general solution, and these are just some sketches of the family of solutions. I won't do any more sketches for these, but that is just to show you. Let's look at the next example. Okay, so we've got to find the general solution of the differential equation dy by dx equals minus, and then 2x plus 1 and 2y minus 2. So again, now, get my y's on one side and then my x's on the other side. And then I had a minus, so I'll apply it to this right hand side. Let me just redo that one. So minus for this minus that's outside of my fraction. So now I need to integrate these. So 2y will go to 2y squared over 2 minus 2y. And then I've got minus, I'll just put brackets up, and 2x squared over 2 plus x plus c. And I can put the brackets around it all, or I can put the brackets around this bit, and because that constant can just be anything. Yeah. Or I can jump straight in without the brackets and put that this is a minus and this is a minus there. Okay, so there's a few different ways in which we can do it. But when you are doing two integrations, okay, there's only going to be one constant, because if you had a constant on this side and a constant on this side, you could put them together, combine them together to just give you one constant. So it makes no difference which side you put the constants on, but in general we put the constants on the right. Okay, so this is my general solution. Now, usually in an exam, if they want it in a particular form, they'll give you an idea of that form. Now, I'm just going to tidy this up. So we got y squared minus 2y equals minus x squared minus x plus c, and this is y minus 1 squared minus 1. And if I take my x squared and my x to the other side, actually let's do that first. So y squared minus 2y plus x squared plus x equals c. y minus 1 squared minus 1 plus x plus a half squared minus a quarter equals c. So here I've got a circle. So my minus 1 and my minus a quarter is going to give me minus 5 quarters. So c plus 5 quarters. And then y minus 1 squared plus x plus a half squared equals a. We'll call it constant a, where a equals c plus 5 quarters. So I've got a circle, centre, minus a half 1. Really I should write these the other way around. There we are. So yeah, minus a half 1 radius root a. Okay, so that is, then I can do my sketches where a will be certain values, and that will just give me different radiuses, but then this is the center of the circle. Okay, but this is the general solution of the equation, and obviously if I had to draw or sketch members of the family of solutions of curves represented by this general solution, it would just be a series of circles, center minus a half 1. Okay, but obviously we're not going to do that. But that is the general solution of this differential equation. Let's have a look at another example. So similar one to the last one, minus y over x, but it's going to produce something slightly different this time. So that's going to be 1 over y on the right, and that's 1 over x dx, sorry, on the right, 1 over y dy on the left, I should say. So this is going to give me log y, and y is obviously in a modulus sign, minus log x plus c. Now, you can, in a lot of cases, use the constant as a log, so like log c or log a. So you can do that, but in this case, what we can do is, if we keep it as a c, we can bring my log x onto the left. Sorry, that's not a times, that's a plus. And this is log xy equals c. So that means that xy equals e to the power c. And this xy is in the modulus sign. Okay, which means that y can be plus or minus 1 over x. Now, if we let a equal e to the c, so that will then be times by a. Okay, so we've got y equals plus or minus a over x. And we need the plus and minus in at this point, because this e to the power c is only a positive value. But because of obviously the modulus sign, we could actually have negative values in here. So we need to make sure that we do put our plus or minus in, because this can only be positive. If this could have been negative, then we wouldn't have needed the plus or the minus. So that's that solution done. Okay, and you can see that we can freely, change anything that's a constant into just a single letter as the constant. Okay, and that will make it easier then, in this case, to sketch these graphs if we needed to sketch them. Now let's look at the final example. So this example's in two parts. Part A is find the general solution. So let's do that first. So dy on the left, and we've got 1 over, and I'm going to change the root x to x to the power of half dx on the right. So x to the power of half, 1 over x to the power of half is x to the minus a half. Okay, so just changing that, then we get y equals, so add 1 to the power, x to the power of half, divide by a half, so that is times 2 plus c. So this is what we've got, y equals 2x to the power of half plus c. That's my general solution there. Now this one is find the particular solution. So when x equals 4, y equals 5. So we substitute that in. So 5, 2 times 4 to the power of half plus c. So that's 5. And that is going to be 4 plus c, so c is equal to 1. Therefore, the particular solution is 2. Now, I'm going to write this as root x rather than x to the power of half plus 1. Just because normally I would write it up here, because where possible, I'd always like it in the same form as the question. And then we have it. So the general solution, this, or y equals 2 root x plus c. And then the particular solution in this case when I substituted in my conditions. And there you have it. This is the start of first order differential equations, and I think you'll agree that this is something that's very familiar to you. So if you found the video useful so far, hit that like button, subscribe if you're yet to subscribe, and if you're willing and able to help me out and help me make these videos, then please consider hitting that join button. Okay, it does enable me to potentially, do less work as a teacher and a bit more work as creating videos, or that's the aim of it. So please consider helping me out there. Now let's look at the questions. So since the start of this is quite easy, I've just gone with 2 questions here. Few parts to question 1, and then question 2, a straightforward one, fairly straightforward, with a particular solution afterwards. So pause the video now. Okay, hopefully you've had time to have a go at those questions. Let's look at the solutions. So dy stays on the left, and then we've got 5x dx on the right. So this gives me y equals 5x squared over 2 plus c. And that is it. That's the general solution of that differential equation. Let's look at b. So dy will stay on the left, and then we have 3x squared dx on the right. So this is giving me y equals 3x cubed over 3 plus c, which is y equals x cubed plus c. And that is then the the general solution of that differential equation. Let's have a look at C. Now C is involving x's and y's, so let's take the y to the left, so it becomes 1 over y dy, and then 1 over 2x dx on the right. So this is going to be log y equals half log x plus c. Now, this isn't particularly nice in this form. So, I could, for example, have it log y equals log root x plus log, let's call it b. So c equals log b. And then log y equals log b root x. So that means that then y equals b root x, or y squared equals b squared x, where, for example, a could be equal to b squared, and that will give me y squared equals ax, or if you recognize this, that b squared could equal 4a, and then I got y squared equals 4ax, and if you recognize that, that's a parabola, obviously with the origin at 0, 0, and the directrix at minus a, x equals minus a, focus at a comma 0, and so on. So if I needed to sketch it, converting it down into like this form would enable me to sketch this graph. Okay, so you might have stopped up there. In a lot of these general solutions, it's better not to have like a log y equals, so get down to like this form, okay, which then you could write in this form if the question so asked you. So I'm just giving you an example there, but you should be at least down to this form, so you got a y equals. Let's have a look at D. So this one's going to be y dy x dx. So that is going to be y squared equals x squared plus c over 2. So almost forgot that. Or I could write this as y squared minus x squared equals 2c. And that 2c obviously I could change into a normal, like another letter like a. And this y squared minus x squared, I could do difference of two squares. So y minus x and y plus x. So for example, y minus x, I'm just giving you extra examples here, and y plus x. Okay, and then when this equals 0, then it'll be, straight lines with asymptotes. So there's, there's quite a few different things here, but ultimately that 2c, depending on which value it is going to give you different types of graphs. But in this case, because we've got a y squared and a x squared, it's best to leave it in terms of like this form or this form. Okay, and this form is more for if you had to sketch it and you were given values for x and y and so on, or you were told that this equals 0, then you could sketch it quite easily from there. So that is D. Let's have a look at E. So dy stays there, and we've got cos x dx. So cos differentiates the minus sign, so it integrates the positive sign plus c. So that is just the general solution there. And obviously if you had to sketch it, the plus c would just make the sine graph go up or down. Translate up or down. Nice and easy. So that's A, B, C, D and E from question 1. Let's now look at question 2. So we've got, right, let's go with 1 over y dy and 2 over x dx. And this 2 I can take outside of my integral. So I've got log y equals 2 log x plus c. And then really these should be in modulus signs. So this is going to be log y equals log x squared plus c. And then this plus c I can turn into, and I could have done this right from the start, but a log a. So now we've got log y equals log ax squared, which means that y equals ax squared. Obviously up here when I went to the x squared, I could effectively get rid of my modulus sign because, you know, x squared is positive. Okay, so, you know, I could effectively get rid of it then. But yeah, there we have it, y equals ax squared. Now B is find the particular solution when x is 3 and y is minus 18. So minus 18 equals a times 3 squared. So minus 18 equals 9a. So a equals minus 2. So that is y equals minus 2x squared. And that is the particular solution to this differential equation. And there you have it, nice and easy. Okay, so relatively easy introduction into differential equations. We will look at some other forms of differential equations, but the first order differential equation will only ever have like a dy by dx in it. Later on, in the next series of videos, when we look at second order differential equations, then we start seeing the d2y by dx squared as well coming into these differential equations. But for now, the first order differential equation is just the dy by dx. And in the next video, we'll start looking at the kind of questions which are more common in the exams. Okay, so stay tuned for that. And just before you go, final reminder to like, subscribe and join. Peace out.